Okay, so as we discussed in the previous lecture as well, this week you have the take-home exam one. Please make sure that you submit the take-home exam one by September 29, that is next Monday. And of course, the solutions to homework 2, solutions to homework 1, as well as the similar problems of homework 3 that I have posted on Canvas, they will be very important in solving some of the exam 1 problems. All right. So going back to what we were discussing in the last lecture, we were discussing this particular problem, which is similar to some of the questions that you have on your homework number 3. So of course, as we discussed in the last lecture, the capacitor here, the C1, the C3, they are called coupling capacitors because they couple the AC signal from, for example, the input side. So you have this input signal connected to your circuit, which is coming from this AC voltage source, let's say. And why is this a AC voltage source? Because if it were DC, the DC will not even pass through the capacitor because capacitor offers infinite impedance at DC. The impedance of the capacitor is 1 upon SC or 1 upon j omega C, which is infinite when omega is equal to 0. So this capacitor has to be a short at your frequency of interest. Similarly, C3 capacitor has to be a short at your frequency of interest, as well as C2 capacitor has to be a short at your frequency of interest. Because if C2 is not a short, then this R1 does not go to ground. So the bottom terminal of the R1 is not connected to ground. And you know from your uh, previous understanding of non-inverting amplifiers, non-inverting op-amp based amplifiers, that as you are providing your input to the non-inverting terminal or the positive terminal of the op-amp, the feedback needs to be placed between the output and the negative terminal or the inverting terminal of the op-amp. So that's with this feedback resistance R2. But unless you have this R1 resistance connected to ground, you will not get that gain of 1 plus R2 over R1, right? You will still get, if for example, the bottom terminal of the R1 resistance is not connected to ground. So basically you have an infinite resistance from this V minus terminal to ground in that case. Okay. And if it's an infinite impedance, so R1 becomes infinite if C2 is open. And in that case, you're 1 plus um, R2 over R1. So basically the gain of this particular circuit, because this is a non-inverting amplifier, that's basically 1 plus R2 over R1, right? Now, uh, capacitor, if your capacitor is a short, then only you see that this 1 plus R2 over R1 makes sense because then the value, the impedance of this total R2 in series with R1 in series with C2, the total impedance is equal to R1 when C2 is a short. And then this equation makes sense. However, if C2 is an open, the impedance of R1 in series with C2, that's basically infinite. So instead of R1, you have an infinite impedance in that case, which happens at DC actually. So at DC, your gain is actually equal to 1 in this case, or very close to 1. So at DC, your frequency is very close to DC. What does that mean? That means that whatever voltage you have at the V minus terminal of the op amp, that is the inverting terminal, the same DC voltage is available at the output terminal as well. And that makes sense, right? Because if this path had not existed, if this R1 in series with C2 had not existed, which does not exist at DC because C2 is an open, so, and you already know that there cannot be any current flowing into the negative terminal or out of the negative terminal of the op amp, which means there is no current flow through R2 in that case, which means that the voltage at the left side of R2 and right side of R2 has to be the same. So from that perspective also, you know that the negative terminal's DC voltage has to be the same as the output's DC voltage. So that's how the DC bias points are fixed. Of course, at the input side at the V plus terminal, the input bias, DC bias is fixed by this RB1 and RB2 resistors. Right? So that's something we already discussed in the previous lecture. One other thing that we discussed was what are the poles? What are the poles that needs to be considered for this circuit? And of course, as you know that this C1 in series with some kind of a resistive network connected to ground after that, that forms a high pass filter. Again, this C3 along with this RL, that forms a high pass filter. This C2 also effectively creates a high pass filtering effect because unless the frequency is high enough, the C1, C2, and C3 capacitors are not short. And if they are not shorted, then you don't have the same circuit as the non-inverting amplifier that you have learned before, right? So it works as a non-inverting amplifier only after a certain frequency, which means everything is high-pass filter, right? Now, in terms of the high-pass filtering, if you plot your frequency on the x-axis and the transfer function on the y-axis, because, uh, okay. So let's say your transfer function is on the y-axis. So because you have three different poles, so let's say 1, 2, and 3. So something like that. And after a certain frequency, you get a fixed constant value. So let's say one pole is here, the other pole is here, the other pole is here. There could be three different poles. Of course, after the first pole, you have a minus 20, or in this case, basically 20 dB per decade slope. Then you have a 40 dB, then you have a 60 dB per decade slope. And on the right-hand side of this third pole, you have basically a constant transfer function. So you are interested in only this part, right, which is on the right side of the dominant pole. The first pole is called the dominant pole because that determines the cutoff frequencies. So in this case, in the question, it is asked that you have to choose values for C1, C2, and C3 to set the lower cutoff frequency or the lower minus 3 dB frequency to 50 Hertz. Why is it called the lower cutoff frequency? Because you have a high-pass filter, so you only have a cutoff on the lower side of frequency. So it's a lower cutoff frequency, which is 50 Hertz. So you want to set your dominant pole at 50 Hertz. The other poles can be at some other locations. Let's say you don't care about those because you want to create a first order system effectively. So for the frequencies of interest and for nearby frequencies, it should act as somewhat like a first order filter, which means that you only need to have one pole at 50 Hertz. The other poles need to be at much, much lower frequencies. So they can be, let's say, 10 times lower. In that case, they are 5 Hertz, 100 times lower, so 0.5 Hertz, and so on. But 50 Hertz will be the dominant pole frequency. Yes, so there is a question on Zoom that can you say that C2 makes a high-pass filter because it does not let amplifying the signal until a certain frequency, right? At lower frequencies, it does not let the circuit amplify those signals. At lower frequencies, C2 acts as an open. At zero, it's a perfect open. Zero frequency, it's a perfect open. And that is the reason why we are saying that all three capacitors, along with their resistances, associated resistances, they work as a high-pass filter. All right. And what we also discussed at the end of the last lecture is how to analyze these three poles. The way to do that is consider each of these capacitors one by one. They consider each one of them separately and see how much resistance is associated with the capacitor. And 1 upon RC will give you the value of the pole, right? So if you consider C1, on the left side of C1, you have RS connected to ground. And of course, when you are looking at Thevenin equivalent resistances across the two terminals of the capacitor, that's what basically you are looking at. What is the Thevenin equivalent resistance across the two terminals of the capacitor when you consider, let's say, the first capacitor C1. So that's the R Thevenin that you want to take a look at. On the left side, you have RS. On the right side, what do you have? On the right side, you have RB2 connected to ground, definitely yes. But you also have a RB1. So this is RB2, which is connected to ground. But you also have a RB1, which was connected to VDD or VCC in this case, the supply voltage. However, keep in mind for AC analysis, Thevenin equivalent resistances will be using for AC analysis in this case. And of course, you are doing an AC analysis because you are looking for the pole. The pole is a AC concept. At DC, there's no concept of poles. So if you're doing AC analysis, in terms of AC, all your DC voltages are virtual ground. So even your supply is a virtual ground when you're doing an AC analysis. So your RB1 actually goes to this virtual ground. So what does that imply? That implies your RB2 and RB1, they are in parallel, looking on the right side of this capacitor, and looking on the left side of the capacitor, you have RS. So what is the overall capacitor that you see, that the C1 capacitor sees? The overall resistance that you see is RS plus RB1 in parallel with RB2, because you have your grounds all connected. On the left side, you have RS. On the right side, you have RB1 in parallel with RB2. So those two in the loop, they are coming in series. So C1 sees this much. How much does C2 see? C2 will be So again, you're looking at the Thevenin equivalent resistance from the C2 capacitor. Of course, the other terminal is connected to ground. So you'll be looking into whatever is the capacitance that you're seeing looking up from the C2 capacitor. And what is that resistance? That resistance is only R1. Why? Because, again, think about that because of the virtual ground properties, all you'll be seeing at this point is R1. You can do the math, you can calculate it. I'll not go through the math again because we have solved similar problems quite a few times in the class. So C2 will see only R1. And finally, what does C3 see? C3 will see RL on the right side, but on the left side, you have multiple resistors connected to it, R2, then R1, then so on. However, there is a zero resistance path through the output of the op-amp. Because there is a zero resistance path, all these resistances will not matter. So on the left side of C3, you just see a zero resistance. And on the right side of C3, you see RL. So overall, you see 0 plus RL, which is equal to RL. Now you create, so basically that's what your C1, C2, and C3 will see. It will see this much amount of resistances for each of the capacitors. Now you are asked that, okay, find out the values of C1, C2, and C3. Your R values are given, resistance values are given. Find out the value of the capacitance so that the lower cutoff frequency is 50 Hertz. So for that, again, as we discussed, there has to be only one dominant pole. That means you can only consider one of the RCs. So 1 upon RC would be your dominant pole. Only one of the capacitors should contribute to the dominant pole. Others should contribute to non-dominant poles. And by non-dominant poles, you mean that they have to be far away from the 50 Hertz. They should be much smaller than the 50 Hertz because this is a high-pass filter. For a low-pass filter, they have to be much away from the dominant pole again. That means they have to be much, much larger than the dominant pole for a low-pass filter. Because this is a high-pass filter, the non-dominant poles have to be much, much smaller than the dominant pole. Because again, remember, how does the high-pass filter and low-pass filter looks like? High-pass filter looks like this. So this is the dominant pole. Anything happens on the left side has to be much lower frequency as compared to the dominant pole. If it were a low-pass filter, that is, you are considering this part, again, the dominant pole over here is here at this point, and then you want to consider any other pole, non-dominant pole, at much, much higher frequencies if it were a low-pass filter. So that is the reason why, let's say you are choosing C2 to create the dominant pole. You can choose any other capacitor as well. It does not matter. Everything is a correct answer. You just have to choose one of them. If you choose C2, of course, the resistance associated with C2 is 1K. The frequency at which you want to place the dominant pole is 50 Hertz. You can calculate your C2. Similarly, you can calculate your C1 and C3. But for those, you have to consider that you want non-dominant poles. So let's say you want a 50 Hertz divided by 10, or again, a 50 Hertz divided by 10. So much, much smaller than the dominant pole frequency. That's what you want for C1 and C3 related poles. But the resistances connected with C1 is about 500K. For C3, it's about 50K. And using those values, you can find out what would be your C1 and C3. So you have a very similar problem in your homework number 3 as well. So this is just I'm showing how to solve those kind of problems. Please look into problem number 2 as well. It's again very similar, but these graphical representations give you a very good idea what would be the voltages at each of these points. So here you're providing a triangular-like waveform, and Vs is basically the voltage at this point, right? Vs as a function of t is the voltage at the source. Now, of course, as you know, your V plus will be set at 5 volt DC because there is a equal voltage division through these two 1 mega ohm resistances. So V plus will be set at 5 volt DC. So you'll have, and because of the virtual ground property, your V plus and V minus will be exactly the same. So both of them will be around this 5 volt DC. But again, the amplitude of the signal, the peak to peak amplitude will be this 0.2 volts, or the single-sided amplitude will be just 0.1 volt. So from 5.1 to 4.9. Now your A infinity in this case is 1 plus R2 over R1 because this is a non-inverting op-amp. R1 plus R2 over R1 is going to be 41. If you calculate the numbers, R2 and R1 are given. So you know that your output will be 41 times higher than the input, but the output DC level is also at 5 volt. That's what we established in the previous part of the problem. So you have a 41 times of 0.1 volt on each side. So your signal excursion will be 9.1 volt to 0.9 volt. So that's how the signal will look like at the output side. Okay. So just look at these graphical representations. There's another problem which is showing the same thing, but here you'll see that if your gain is too much, or if your output signal excursion is too much, if it is higher than the supply voltage, if it is higher than 10 volt, which was the supply voltage in this case, and lower than 0 volt, which was the voltage for the ground in this case, you'll see this kind of a clipping. And we'll also see more clipping architecture. So when we study diode, we are going to start with diodes in today's lecture, but please look into these problems. There's also a summary that I have uploaded on Canvas. So if you go back over here, there's a non-ideal op-amp summary. I'll just quickly go over that, but it's mostly some of the things that you already know. Okay, so it basically says how you're going to use the feedback, the concept of feedback, the concept of loop gain and ideal gains and so on. So your feedback equation was A divided by 1 plus A beta, which is equal to 1 over beta divided by 1 plus 1 over T, where T is the loop gain, T equal to AB is the loop gain. And you can find out your closed loop gain and your ideal scenario for the closed loop gain, which is equal to 1 over beta if your A is infinitely large. So again, just a repetition of what you have learned. So A infinity divided by 1 plus 1 over T. This was just an example. Again, something that I think we have gone through in the class. A infinity in this case is going to be minus of R2 over R1 because this is an inverting op-amp architecture. So minus of R2 over R1 is going to be minus of 20 kilo ohm divided by this 10 kilo ohm. So minus 2 is going to be your gain, or A infinity in this case, if the op-amp is ideal. To find out R out, of course, you'll remove your VS, the original independent voltage source, and apply either a voltage source at the output, measure the current, or apply a current source at the output and measure the voltage. The ratio of those two will be your R out. Since the op-amp's output has zero resistance and there is a path through the op-amp's output terminal, the R out is going to be zero in this case. What is going to be R in? Again, as you know that because of the virtual ground property, the voltage at the inverting terminal and the non-inverting terminal will be exactly equal. Because there cannot be any current flow into this positive or the non-inverting terminal of the op-amp, the voltage at the top of resistance R3 is going to be zero because the bottom of resistance R3 is also connected to zero. And because of the virtual ground property, the voltage at the inverting terminal of the op-amp will also be forced to zero. If that voltage is forced to zero, the current through the 10 kilo ohm resistance is going to be forced as Vs divided by R1. So the current that is coming out of Vs is Vs divided by R1. Now, according to Ohm's law, your resistance looked into this particular terminal is going to be the voltage divided by the current. So Vs divided by Vs over R1. And that eventually gives you the R1 resistance. So remember that it's the fact that the op-amp forces the virtual ground property and forces the voltage to zero. It does not create a zero resistance path to ground. It creates a voltage which is equal to zero, but it's not an actual ground. It's a virtual ground. So no current will go into it. Current will eventually flow in this path. However, the voltage is forced to zero at this point. Finding out T, again, you can just draw the internal circuitry of the op-amp. You want to find out beta. So you'll start from, let me go through this one by one. So you start from the dependent voltage source over here, or you can just replace this dependent voltage source with a test voltage source, which is Vx, and try to find out what is connected after that to eventually come up with the factor of, or the portion of the voltage that goes back to the input. First thing you see is the RO resistance, that is 1K. So if the resistance after RO is denoted as RY, let's say I don't know what that resistance is, but I'm just representing it as RY. I don't care the value of it, but if it is RY, then the V1, the voltage at this point is going to be RY divided by RY plus R naught times Vx. Just a very simple voltage division. Next, you have this R4, 4K resistance going to ground, and then you have a 20K resistance R2 going back toward the input side. So sometimes I have seen, like, if it is not very intuitive or convenient to think about the flow of voltages or currents from the output side to the input side, you can just redraw the circuit in this manner. If it is easier for you, just consider everything is flowing from left to right, which is very easy to intuitively understand. So start from the Vx, which is the leftmost component, and then try to see what are the voltage division along the path. Okay. So you have this 20 kilo ohm R2, and then again after R2, you have some sort of a very complex network of resistances. So let's say you don't want to deal with that right now. Let's just say that resistance at this point is Rx. If that is Rx, then you have another voltage division over there. V2 is going to be Rx divided by Rx plus R2 times V1. So which means V2 is going to be the multiplication of these two voltage divisions times Vx. And then you finally find out what is connected after V2. After V2, you have the Ri resistance across which you want to find out the voltage eventually. So that's a 80 kilo ohm resistance. And then there's also R3, which is a 30 kilo ohm resistance connected to ground. So you have your Vy, which is Ri divided by Ri plus R3 times V2. So you represent your final Vy, or the voltage at the input terminal, as a function of V2. Now you know V2 as a function of V1 and V1 as a function of the original Vx voltage. So you can find out your Vy voltage as a function of Vx, and then this is basically your beta. This is the feedback factor. So you find out your feedback factor beta as Vy divided by Vx, and then your A times beta is basically the multiplication of your gain of the op amp, which is 400 times this beta. So just a very simple way to calculate your loop gain. We also looked at the frequency response, and all it says is that if your gain is going to be reduced by 1 plus A beta, your pole frequency, or basically your bandwidth, is going to increase by the same factor 1 plus A beta. So your homework 3 has a few problems related to it, but the answer is going to be very simple. Gain reducing by 1 plus A beta, bandwidth increasing by 1 plus A beta whenever you have a closed loop operation. Okay. All right. Any questions on non-ideal op amps till this point? If not, the next question that we are going to ask ourselves, that why are there non-idealities in the op amp, right? I mean, we just say in 3111 we learned about ideal op amps, and we could be happy with just ideal op amps, right? Why there is a need to understand and analyze non-ideal op amps, right? And that is because realistic op amps are non-ideal. And yeah, thank you. So realistic op amps are non-ideal. And if realistic op amps are going to be non-ideal, the next question that comes to mind is that what determines those non-idealities? Why is the realistic op amp non-ideal? And that comes down to how the op amp is actually designed. So what is there inside that black box, the triangle, right? So we just consider that as a black box. We don't know what is there inside of the op amp. So in the rest of the course, actually, we are going to learn what is there inside the op amp. And there could be circuits that are built using diodes, circuits that are built using MOSFETs or BJTs inside the op amp. And we are going to look at those devices for the rest of the semester. And then finally, we'll design an op amp with those components, right? That would be, I think, almost the last homework that we'll have. We'll be designing the op amp with those components inside of the op amp. And because those components are non-ideal, they result in a lot of the non-idealities that we have seen till now. Okay. So let me start with the first type of devices that we'll learn in this course, and they are going to be called diodes. So this is all the material I have taken from Bolster's book, but yeah, I mean, everything that is required is there in this PPT. So you don't need the book separately. So if you just go through the PPT, you'll understand what is going on. Okay, so what are diodes? Diode is basically a two-terminal device, similar to your resistors or capacitors. They are also two-terminal devices. The diode is also a two-terminal device. So you have a, let's say, a positive terminal and a negative terminal. So basically you're applying a positive voltage at the positive terminal and a negative voltage or a lower voltage at the negative terminal, right? So the current flow that you're expecting is in this direction. Now, the funny thing about diodes is that the diode would ideally conduct only in one direction. Again, ideally means you already understand that there are non-idealities with the diode as well, and it will also conduct a little bit in the other direction. But ideally, the diode conducts in only one direction. So if the voltage is higher on the left side and the voltage is lower on the right side, and if the diode symbol looks like this, remember that this is the symbol of the diode. Um, the left side of this symbol, left side of this triangle is going to be the positive terminal, and the right side of this bar that we see over here is going to be the negative terminal. And what this bar actually represents is that there is kind of like a wall on the right hand side. So if you're trying to push current from the right hand side toward the left, it will hit this wall and it will not go through anymore. That's why the symbol is drawn like this. Okay. But when the current is coming in like this, it's basically going through, for example, this funnel, and then it becomes, let's say, it's coming out of this funnel, and then it can probably go through this wall if the way you can think about it is that if the current is going through a very small window, then if there are holes in the wall, the current can actually go through that. However, from right to left, all it sees is this big large wall, and then current cannot go through. So the diode will act as a short circuit whenever the current is flowing from left to right in this diagram. What that means is that the diode's positive terminal is connected to a positive voltage and the negative terminal is connected to a negative voltage. And we'll learn later that it's called forward biasing the diode. We learned about biasing, and biasing is very important to make sure that the circuit operates correctly. Forward biasing means that the diode will be operating correctly. On the other hand, this other scenario, when you have a higher voltage connected to the negative terminal of the diode, the cathode of the diode, and a lower voltage connected to the positive terminal or the anode of the diode. In that case, the diode acts as an open circuit. So this is very different behavior from resistors or capacitors because, okay, if you don't consider electrolytic capacitors, but let's say normal capacitors or let's say resistors, it does not matter which direction the current flows. Current can flow in both direction and the value of that will be same. However, for diodes, this is very interesting. This is a unidirectional circuit. Current can only flow in one direction and cannot flow in the other direction. Okay, so that's the basic difference from any bidirectional circuit element with an unidirectional circuit element, which is the diode. Now, as we already discussed, that there would be two regions for the diode. One is the region of conduction and the region of non-conduction. So, of course, if you say that the voltage across the diode is the voltage between these two terminals, so basically between the anode and the cathode, or the negative terminal, or the positive terminal and the negative terminal of the diode, let's call that voltage as VD. That's just subscript stands for diode voltage. So VD stands for diode voltage. And let's say you want to measure the diode current, ID. If the diode is forward biased, that means you're connecting a higher voltage to the positive terminal of the diode and a lower voltage to the negative terminal of the diode, like it is done in this particular figure, you will see a large amount of current flow through the diode. The diode acts as a short. On the other hand, in the non-conduction region, so basically you're connecting a lower voltage at the positive terminal of the diode and a higher voltage at the negative terminal of the diode. In that case, the diode ideally will work as an open circuit. So whatever voltage you provide, whatever VD you provide, and you see that you're considering the VD on the negative side, right? Whatever negative VD you provide. And why VD is negative? Because VD was originally defined as the voltage between the positive terminal of the diode and the negative terminal of the diode. So if you are reversing it, VD becomes negative. So when VD is negative, ideally the current through the diode should be zero. So you should see only zero current, and nothing else in this case. So all the current is zero ampere, and all the voltage drop is happening across the diode. Right? So you are applying a voltage across the diode. So of course there has to be a voltage drop, as you know from KVL, that there has to be a circuit component that accommodates that voltage drop. So what is the circuit component here? It's just the diode. So all the voltage drop is happening across the diode, but the current is 0 ampere. The resistance is defined as voltage over current, right? VR over IR. Now, since the current is 0, this resistance is infinitely large. And infinitely large resistance means the diode is acting like an open circuit. In the conduction region, the voltage across the diode is 0 volt. The diode is acting like a short. And for a short circuit, the voltage across the short circuit is 0 volt, because that's the definition of a short circuit, that all the voltage is available on the other side of the component as well. The current is infinitely large. Again, for a short circuit, you know that the current will be infinitely large. The forward resistance is Vf over If, again, voltage over current according to Ohm's law. And that forward resistance is 0, because now your voltage drop is 0, but the current is infinite. So the diode is actually acting just like a short. Now you can create the diode with different kind of semiconductor materials. Why do you need a semiconductor material? Because again, you saw that it's a very interesting property for the diode. It's not a conductor. It's also not an insulator. The value of the current that flows through the diode that is determined by the voltage and how you apply the voltage across the two terminals. So it's somewhere in between a conductor and an insulator. And what is between a conductor and an insulator? It's called a semiconductor. There could be different materials, for example, silicon, germanium, gallium arsenide. These are the materials that act as semiconductors. So they are not fully conductors. They are not fully insulators as well. They are somewhere in between. So diodes are usually built using this kind of semiconductor material. And if you take a course in device physics or semiconductor physics, you'll learn more about all these material, which we are not going to cover in this course. We'll just assume that we are using semiconductor-based materials for building diodes, MOSFETs, and so on. Okay, now one interesting concept regarding semiconductors is doping. What does doping mean? It's basically enhances the capability of the semiconductor eventually, and that's what is meant by doping in this case. So there are two types of doped semiconductor materials, N-type and P-type. What do they mean? In general, whenever you talk about any material, the number of electrons and holes in the material is going to be equal, right? The number of electrons and holes are going to be equal. What does electrons and holes mean? Of course, you know electrons could be on the conduction band of a material, which means they can flow from one particular atom to another atom, right? If it is in the conduction band. If it is in the valence band, they're very much closely tied with the particular atom. So it needs a particular amount of energy to go from valence band to conduction band. And only if it is provided that particular amount of energy, it can go to the conduction band and then move around. So a valence band electron cannot move around, but a conduction band electron can move around. Normally in a device, or normally in an atom, there are only electrons. There is no concept of holes, right? But whenever you have multiple types of devices, multiple types of material together, you may create absence of electrons, which are going to be called as holes. Now, it might seem like a foreign concept here, but it's easier to think about in terms of electrons. So let's say for N-type electrons, what we'll have is an excess of conduction band electrons. What is meant by, let's see if I have a, okay, I do not have a slide separately. Let's just try to understand what is meant by N-type semiconductor then. So if you look at the band structure of or the crystal structure of the silicon, so a silicon atom, if you look into the periodic table, a silicon atom is kind of exactly in the middle columns of the periodic table. You'll see that it will be, if you look at the crystal structure, the silicon atom looks like this. that it has 4 valence electrons. Each silicon atom has 4 valence electrons. And then they can bond with 4 other nearby silicon atoms, because they will share 1 atom each and create that strong uh, double bond between the silicon atoms. So every silicon atoms, for example, the silicon atom over here is also connected with 4 other silicon atoms like this. This is also connected to this. There would be a silicon atom over here, and so on. So that's how the crystal structure of silicon looks like. It's a very much regular structure, but you'll have 4 bonds with nearby silicon atoms. Now, let's say I put some amount of impurity into pure silicon. Let's say I introduce some phosphorus. So instead of, let me clear some of it. So let's say instead of this atom, I somehow introduce a phosphorus atom over here. And again, if you go back to your periodic table, which you learned in your high school chemistry, for example, a phosphorus atom will have 5 conduction band electrons. So there is 1 extra bond for phosphorus. It can bond with 4 silicon atoms on 4 sides. So let's say there is a silicon here, there is a silicon atom here. But it will still have this 1 extra valence bond electron or outer shell electron. And that electron cannot bond with anybody else. And that electron can move from, let's say, because this is an extra electron and which is in a conduction band, it takes very little amount of energy for that electron to detach from this phosphorus atom and then move around in the overall structure. And if an electron moves around, you have current. Current is nothing but flow of electrons. Right? So this n-type n-type material will have an excess of conduction band electron. There would be 1 extra electron which will be there because of the existence of this phosphorus atom. And if that electron moves around, you'll have an excess conduction band electron, eventually creating a current. Okay. Yep, I guess there was a comment on chat where George has described n-type and p-type electrons. So you guys are already very familiar with this concept. I'm just trying to go through them in a very layman's language in case someone is not very familiar with n-type and p-type doping. But I guess most of you are already very familiar, so I may not have to go into details of it. Now for p-type material, it's very similar. It's just that instead of, let's say, a phosphorus atom which has an extra electron, you might have something like a boron. Boron has 1 less electron. It has 3 electrons on the valence band on the outer shell. And what that means is that there is an absence of electron. There was 1 additional silicon atom which wanted to bond, but you don't allow it because boron does not have that extra electron. It has only 3 electrons in its outer shell. So p-type material will have impurities, and impurities are coming because of excess valence band holes, right? And holes means absence of electrons. So what can happen is that some of the free electron in the overall structure, they always move around. Even in the silicon crystal structure, there are always some free electrons which are moving around. And that's why the silicon is a semiconductor. For an insulator, you do not have those free electrons moving around, and that's why insulator do not conduct current. For metals, you have a lot of free electrons moving around, and that's the reason why metals always conduct current. Semiconductors have some free electrons moving around, and that's why it somewhat conducts current. It is somewhere in between metals and insulators. But if you dope the material with excess conduction band electrons, so let's say you create an n-type material with phosphorus impurities, for example, or you create p-type materials with boron impurities. In that case, what would happen is that you'll get excess electrons or excess number of holes. So you're just increasing the number of free electrons that can move around. And that's how you are increasing the conductivity properties of normal silicon, or basically just if you just had silicon, it would not be as conductive. But creating an n-type material or a p-type material through doping, that is introducing some amount of impurities, you will be increasing the conductivity of the material. Okay. Now, having said that, let's say you have a p-type material and an n-type material. Okay. And let's say you just fuse them together. You create a structure that half of it is p-type and half of it is n-type. That is generally called a p-n junction. And if you look into the p-n junction, the excess conduction band electrons on the n side. So let's say, oops, sorry. Let's say this is your p-n junction. This is the p-type side, and this is the n-type. So in the n-type semiconductor, you'll have excess conduction band electrons because you're doping it with phosphorus, for example, which has more number of electrons, and there would always be that extra bond or extra electron that can move around. And that is determined, or that is represented with these negative signs over here. And as you see that the negative sign is not enclosed with a circle, what that means is that the negative, which is just an electron, that can move around. Whereas all the positive and negative charges that are encircled, they mean that they are fixed charges which are within an atom. So the atom cannot move around. Right? If the atom moves around, then it will be maybe a liquid or a gaseous material. It cannot be a solid material if the atom moves around. So the atom does not move, but the electrons within the atom can move. Now, for an n-type material, there are more number of movable electrons. And that is the reason why it is an n-type material. There are more number of movable electrons. That means there are more number of positively charged atoms, because the movable electron has come out of the positively charged atom. In the entire material, the number of positive charge and negative charge is equal. So if you just have this n-type material, the number of positive charge and the negative charge has to be equal because it's electrically neutral. It does not create energy, right? So the number of positive charge and negative charge is always already equal in the n-type material, but there are more movable electrons which are indicated by these negative signs, which means the atoms are becoming positively charged. So more number of positively charged atoms in the n-type material. Similarly, in the p-type material, there are excess holes. And these holes are also movable because holes are nothing but absence of electrons. And that point of absence of electron, or the location of absence of electron, that can also move from one atom to another. And so the atoms are becoming negatively charged. So that's why the encircled ones, encircled representations that you see over here, they are the atoms which are fixed and not movable. Whereas the positive or negative signs that are not encircled, those are the movable ones, electrons or holes, whatever you have. Now for the p side, p-type semiconductor, you have more movable holes. So you have more of these plus signs and less number of movable electrons. So less number of these negative signs. On the n-type material, you have more number of these negative signs, that is movable electrons, but less number of movable holes. So this is just the only scenario where you have a movable hole. And that makes sense because the n-type material is generally has the capability of move these electrons from one atom to another, and that's how they conduct current. P-type material, they move the holes from one atom to another, and that's how they conduct current. Okay. However, the atoms themselves do not move. Now, as soon as you put the p and an n-type together, what happens in that case? As soon as you put the p-type material and the n-type material together, the electrons in the n-type material, they will migrate across the junction. The electron in the n-type material, they will try to migrate across the junction. And this electron migration will result in a negative charge on the p-type side of the junction and a positive charge on the n-type side of the junction. Okay. Why is this happening? That is because there are excess holes on the left side. So there are excess holes over here. There were excess holes. There were excess electrons here, and they were very close to each other. Excess holes and excess electrons very close to each other near the junction. So if they're very close to each other, they will just migrate and recombine. So that's why in this region, you see that there are no non-encircled charges. There are no free electrons or free holes within this region. And because the free electrons and free holes create the currents, they are basically the source of the current within the device. You call them the majority carriers. The electron is the majority carrier for the n-type semiconductor, and the hole is the majority carrier for the p-type semiconductor. Of course, there are the oppositely charged, let's say, free electrons or holes as well. So in the p-type material, there are some free electrons. In the n-type material, there are some free holes, but not a lot. Those are called minority carriers. So majority carriers are defined as the carriers which are mostly present in that type material, which would be electrons for n-type and holes for p-type. Minority carriers are the opposite ones. They are holes for the n-type material and electrons for the p-type material. Now, what happens within the depletion region is that the additional electrons or the freely moving electrons within the n-type very close to the junction and the freely moving holes very close to the junction, they recombine with each other. And recombining electrons and holes means you have nothing, because electron was positively charged, holes or negatively charged, holes positively charged. You combine them, you get nothing, right? So that is the reason why very close to the junction, you have a depletion region where there are no majority carriers. There are no electrons, there are no holes as well. And that's why it's called depletion region, because that region is depleted of any kind of majority carriers. There could still be a few minority carriers within the depletion region though, and that actually creates leakage currents, which is again a non-ideality. So you can create, you can have some amount of minority carriers and leakage current within the depletion region, but in general, you will not have any majority electrons or holes within the depletion region when the p-type and n-type are combined together. Now, a diode has 3 different operating conditions, and depending on the operating condition, the width of the depletion region will change, as you'll see. So the diode can have no bias, it can have forward bias, it can have reverse bias, as we discussed in one of the first few slides. What no bias condition means that you're not applying any external voltage. So the diode voltage is equal to 0. The diode current will also be equal to 0, and some amount of depletion region will exist. In reverse bias, what would happen is that you're applying an external voltage across the PN junction with the opposite polarity of the p-type and n-type material. So p-type material, you're applying the opposite polarity. And now you can also think P and N as positive and negative as well, right? So you're supposed to apply a positive voltage to the positive side of the diode. That's the p-type side of the diode. You're supposed to apply a negative voltage to the N side or the negative side of the diode. In that case, the diode would have been forward biased. But because here you're doing the opposite, you're having opposite polarity, negative voltage to the P side and positive voltage to the N side, you will see that what we'll call this scenario is the reverse bias scenario. So what is happening in this case is the following, as you see on the bottom left. The reverse bias voltage is causing the depletion region to widen. The depletion region will be wider as you are applying the reverse bias voltage. Why is that? Think about it. The reverse bias voltage, the positive voltage, is applied to the N side of the diode. Right? And the N-type material had more free electrons. They had more number of free electrons. What would happen to those free electrons? Because the free electrons are seeing this positive terminal of the battery, the free electrons are going to flow into the battery. That means the current is flowing in the opposite direction. That's why you see the current flow is shown like that. But the free electrons are going to flow into the battery. So more and more number of free electrons will deplete from this side, because electrons are going towards right and you're getting depleted of the majority carriers more and more. On the other hand, from the P side, there were these free holes, and those free holes are moving into the negative terminal of the battery. That is just another way of saying that the electrons from the negative terminal of the battery are going into the P side and then recombining with these positively charged holes. So you're depleting the P side of the originally existing holes once again. So you're depleting the free electrons or free holes more and more. That's what you're doing if you're applying a negative or a reverse bias. And that's why we say that the depletion region will become wider if you are applying a negative or a reverse bias. And that happens simply because electrons in the n-type material are attracted toward the positive terminal of the voltage source, and the holes in the p-type material are attracted toward the negative terminal of the voltage source. So that's what is happening when you have a reverse bias. On the other hand, if you have a forward bias, exactly the opposite thing happens. That you are applying a positive voltage to the positive or the p-type material of the diode. You're applying a negative voltage to the n-type or the negative material of the diode. In that case, what would happen just is that your battery polarity is just reversed, right? So the current will try to flow out of the positive terminal of the battery. That means more electrons are coming out of the p side. And if electrons are coming out of the p side, you're creating more and more holes, free holes. Similarly, on this side, more and more number of holes are getting attracted toward the negative terminal of the battery. That means you are getting more and more number of free electrons. So the number of free electrons on the inside is increasing. Similarly, the number of free holes on the p side is increasing because of the existence of the battery, which just forces some amount of current, which is basically flow of electrons into the device. So you have more electrons on the inside and you have more holes on the p side now, which basically says that you're doing the opposite of depletion. So instead of depleting, you're adding more and more number of charge carriers. So the width of the depletion region will be shorter, will be reduced in this case. So the electrons and holes are pushed toward the p-n junction, and the electrons and holes have sufficient energy to cross that p-n junction. So the electrons and holes which are present on the two sides of the p-n junction, they can cross the depletion region and go to the other side and eventually flow to the respective terminal of the battery. So that's what happens when you have a forward bias diode. So with those definitions in place, I think let's stop here for today. And in Friday's lecture, we'll look into some of the math and what happens in the forward bias and the reverse bias for the diode. And let me know if there are any questions. Okay, so someone had asked that, Grant has asked that what is the difference between majority and minority carriers? So the majority carriers are the carriers, charge carriers, which are mostly already present in the system. So for example, for the n-type material, we discussed that the majority carriers are the electrons, right? Why is that? Because you have an excess of conduction band electrons already in the majority carriers, in the n-type material. So they are the majority carriers, that the carriers which are already present. So you don't need to create them forcefully. On the other hand, minority carriers are the other type of carriers. So inside the n-type material, you have more number of electrons, you have excess of electrons, but excess of free electrons, I should say, but there is a shortage of free holes, right, in the n-type material. Similarly, on the p-type, there is an excess of holes, but there is a shortage of electrons. So holes will be the majority carrier for the p-type material, and electrons will be the majority carrier for the n-type material. But holes are the minority carriers for the n-type material, and electrons are the minority carriers for the p-type material. And very easily, you can just think, you can remember it because P means positive, holes are positive. So holes are the majority carriers for P. N means negative, electrons are negatively charged. So electrons are the majority carriers for n-type material. But why it happens, again, that should be explained very well in a device physics class or a semiconductor physics class, that why do they have these excess electrons? And that's simply because, let's say, if you dope it with a phosphorus atom, phosphorus has one additional conduction band or outer shell electron, which can move around. And that creates those excess of electrons for the n-type. P-type, again, you're doping it with, let's say, for example, boron, and boron has one less electron. So you're creating an absence of electron, which is the hole. So depending on whether you have a p-type material or an n-type material, you will have either excess of holes or excess of electrons. So excess of holes for P, those are the majority carriers, excess of electrons for N, which are the majority carriers. On the other hand, shortage of electrons for P, which is the minority carriers, and less number of, again, holes for N, which becomes the minority carrier for the n-type material. So I hope that answers the question. There's another question on what do we mean by holes can cross the p-n junction. So think about this, that when you are talking about current flow, right? So in this case, let's say you have current flowing out of the battery, going through the p-n junction, and then coming back at the negative terminal of the battery. Current flow is nothing but flow of electrons, right? So if current is flowing in this direction, electron is going to flow in the opposite direction. So let me draw the electron flow with red color arrow. So the electrons are flowing from the negative terminal of battery through the PN junction or the NP junction and coming back to the positive terminal of the battery. That's how the electron is flowing. So electrons have to cross the depletion region. In the depletion region, there were no majority carriers. But majority carriers create this current, right? So if you have a lot of carriers, then you create a lot of current. If you don't have carriers, lot of carriers, you don't create a lot of current, right? So within the depletion region, we just discussed and described that there are no majority carriers. And that is why it is called the depletion region. So whatever majority carriers you have, they kind of have to jump through a let's say gap in the bridge. So let's just consider the PN junction as a bridge that the current has to cross, and there is a gap within that bridge, and that gap is the depletion region. So they have to jump and they have to go to the other side. So if the depletion region is large, it's more difficult to jump from one side to the other. Yeah, and that is the reason why your amount of current that flows in the reverse bias condition is very, very low. But in the forward bias condition, the gap is narrow. So there's a small break in the bridge or small, let's say, region where the bridge is broken, for example, broken down. And you just have to jump from one side of the other. So you have to cross that depletion region. And that's what these electrons are doing, right? Unless the electrons are doing that, there cannot be any current flow. So the electrons are coming in at a particular speed. And because they have speed, they're kind of like running toward that gap on the bridge, and then they just jump, they go to the other side, and they can again come back toward the other terminal of the battery. So any of those majority carriers have to actually cross this depletion region, or they should have sufficient energy to cross. So they have to come in running and then cross the bridge, cross the gap in the bridge to go to the other side. Okay. Same with the holes. I mean, holes are just absence of electrons. So whatever you're thinking in terms of electrons, the dual of that can be thought in terms of holes as well. It's just the absence of electrons. Okay, I hope that answers the question. Okay, so with that, let's end for today and we'll start our discussions on Friday. Thank you, everyone.